Justin Miller here, Oxford College Physics. We got a little problem here. Not a problem, because there's a solution, but a little thing to do. So we're going to be looking at induced EMF and induced current. And this is going to be kind of a simple problem. We're looking at a magnetic field that is changing its strength at a constant rate. So we're going to be using Faraday's law of induction, and we'll just go with this. So we're going to take a 20-term conductive loop that is situated such that the plane of the loop is perpendicular to a uniform magnetic field directed into the board. The area of the enclosed loop is 0.3 meters squared, and the magnetic field changes from 0.1 to 0.4 Tesla at a constant rate over a time of 5 seconds. So we've got ourselves some change in magnetic field flux through the area enclosed by the loop, which will thus induce an EMF. And the question is, what is that induced EMF? And then we go on and ask, if the loop has a resistance of 12 ohms, what is the induced current including its direction? And then what constant rate should the magnetic field change such that the induced current is 0.250 amps? So let's just get started with this. As noted, we've got ourselves Faraday's law of induction that says the induced EMF is equal to negative N d phi sub B by dt. Now in this particular case, we're looking at a constant rate of change with respect to the flux. So since phi sub B is changing at a constant rate, we can write that E induced is equal to negative N delta phi sub B over delta T. So we can use this for averages or constants in terms of rates of change regarding the magnetic field flux. So we're going to go ahead and use this. No need to take derivatives here. And what we just want to know is, what do we have going on here? So in our particular case, we've got N as the number of turns in the loop, which is stated to be 20 turns here. And then we've got phi sub B. Well, phi sub B itself is going to be equal to A times B. A being the area of the loop, and B being the magnetic field strength penetrating through the loop. So with this, we've got A is equal to 0.3 meters squared, and then we've got B is what is ultimately changing here. It changes from 0.1 Tesla to 0.4 Tesla over a time of 5 seconds. So when we go ahead and start looking at, well, delta phi sub B, we have phi sub B final minus phi sub B initial, which is going to be equal to A times B final minus A times B initial. And as noted, we have that B final is equal to 0.4 Tesla and B initial is equal to 0.1 Tesla. So we can start putting this all together, and we've got ourselves that delta phi sub B reduces down to this, and delta T itself is just going to be equal to 5 seconds. Delta T is equal to 5 seconds, the time interval over which that change occurs. So we can go ahead and define what the induced EMF is. Now, I'm just going to go ahead and look at the absolute value of this, because the sign is a matter of the polarization. Not really concerned with that. We're more concerned with what is the value of this induced EMF. The sign correlates with the directionality associated with the induced current, we'll say. So let's go ahead and we'll look at this then. We've got ourselves the induced EMF is going to be equal to, let's take the absolute value of that, and just say that this is going to be equal to 20 multiplied by, well, we've got AB final minus AB initial, divided by delta T is what this expands out to be. And then we can stick in some values here, giving us the induced EMF is 20 multiplied by 0.3 meters squared times 0.4 Tesla minus 0.3 meters squared times 0.1 Tesla divided by 5 seconds. So after all of this, I need my calculator. Let me get it really quick. After all of this, we've got ourselves 0.36, it looks like. 20 times 0.3, no. Let's do it here. We got ourselves 0.36 volts is the induced EMF in this particular case. So there we go. So let us go ahead now. So if this was the answer to part A, we'll go on to part B and figure out what indeed, in fact, is the induced current. So once we got the induced EMF, figuring out the induced current is really just a matter of going to Ohm's law. So we've got part B. The induced current, I induced, is going to be equal to the induced EMF divided by the resistance. So simply, this is just going to be 0.36 volts divided by, let me say the resistance is 12 ohms. And well, that just gives us 0.03. So we ourselves 0.03 amps. It's not that much. 30 milliamps. Great. We also want to know what is the direction associated with this induced current. So for the direction, let's go ahead and utilize Lenz's law, which ultimately is a statement about the magnetic field flux and an induced field that produces an opposition to that change in flux. So we've got this magnetic field. It's changing. Say this background field, changing with respect to time. And what I like to think of it as is, since it's increasing from 0.1 Tesla to 0.4 Tesla, it's like these X's are getting bigger and bigger, saying that the field's getting stronger and stronger. It's directed into the board. These X's are getting bigger because it's getting stronger. An induced field pops up to oppose that change in flux. How do we oppose the change in flux? Well, we have an induced field that is, in this particular case, out of the board, so that it produces some flux that opposes the original change. Ultimately, inside this loop, we don't want there to be any change in flux overall. So if it's magnetic field increasing in strength, we have an oppositional field that pops up to counteract the change in flux. And it is this induced field's direction that directly corresponds to the direction of the induced current. So we want to know about the direction of the current that substantiates an induced field that is directed out of the board. So how do we get that? Well, it's going back to the matter of the right hand rule, right? So in terms of directions, we get the direction of B hat due to a current is gotten from an I hat cross R hat relationship. Fingers, palm, thumb. So we need our palm facing into this region. We need our thumb pointing outward in the direction of the magnetic field, and then our fingers are pointing in the direction of the current. So no matter where I am, if I go around like this, in this counterclockwise manner, my palm's facing inward in the region that we're looking at the magnetic field, my thumb's pointing outward in the direction of that field, and my fingers move along in the direction of the current. So in this particular case, we have that this induced current must be a counterclockwise current. So we can put that here. counterclockwise. All right, so we've got one last question with this, and that is, at what constant rate should the magnetic field change such that the induced current is actually 0.250 amps? So when it changes from 0.1 to 0.4 over 5 seconds, we get ourselves 0.03 amps. Probably gonna have to change it a lot faster than that to get ourselves quite a bit more current out of this. So, let's go ahead and look at this. Part C. Well, we want I induced to be equal to 0.250 amps. That's great. Well, that means that E induced, absolute value wise, meaning I induced times R must be equal to that times 25 times 12. Of course, that's just a 3. Must be 3 volts. So this is what we need for the induced EMF, 3 volts out of it. So we go back to Faraday's law of induction. For this constant rate of change, N delta phi sub B over delta T, and then we can open this up a little bit. We've got that this can be equal to N times delta AB over delta T, and we're not changing the area of this, so A is a constant. We can write this then as E induced is equal to NA times delta B over delta T. And think about what we really have here. We have the number of loops times the area times this quantity right here, delta B over delta T. That is the rate at which the magnetic field changes. That's what we want. That's what we're asked for. What rate should the magnetic field change in order to substantiate 0.250 amps? So let's come over here. Set this on up. See what we got. So we know that we need 3 volts in terms of the induced EMF, and well, that is also equivalent to NA delta B over delta T. So we've got 3 volts is equal to 20 times 0.3 meters squared multiplied by delta B over delta T, which gives us delta B over delta T is equal to 3 volts divided by 20 times 0.3 meters squared. So we get out of this, 3 divided by ourselves 0.500. It says volts per meter squared, but this is actually equivalent to Tesla per second. So there we go. There's the rate that the magnetic field has to change at in order to induce a current of 0.250 amps. That's it.